Hi, this is Bob Pryor, and today I'm talking to you about simplifying trig expressions. To start, let's recognize that we have some identities that we are beginning to become familiar with, starting with the reciprocal identities. We know that because they are reciprocal, secant and cosecant, that secant theta is 1 over cosine, and cosine is 1 over secant. And I say cosine, I mean cosine theta, and secant mean secant theta. Of course, we've learned that we can also write these in the reverse order, so that 1 over cosine theta is also equal to secant theta. Likewise, 1 over secant theta is equal to cosine theta. This means that they can be interchanged for each other within an expression. We also know that cosecant and sine are reciprocals. So again, cosecant theta is 1 over sine theta, and likewise sine theta is 1 over cosecant theta. We also have the reciprocal identities for cotangent and tangent, and I'll mention them here. We use them on occasion, but really what we use more often are the ratio identities for tangent and for cotangent. Tangent theta is sine theta over cosine theta. And what we've learned is that we can also write these, any identity, in the reverse order. So sine theta over cosine theta can also be rewritten as tangent theta. Likewise, we know that cotangent theta is cosine theta over sine theta. And now we come to the all-important Pythagorean identities. You know, they're called this because they're based on the Pythagorean theorem. A squared plus b squared equals c squared. And you'll notice that all 7 of these, each term is being squared. Even the 1 is 1 squared. We have our basic Pythagorean identity, the cosine squared theta plus sine squared theta equals 1. Or, if you want, you could write it as sine squared theta plus cosine squared theta is equal to 1. That's kind of the foundation for all of the Pythagorean identities. I did not list here all the square root identities that were also Pythagorean. I'm focusing just on those that are term for term in the form of something squared, like cosine squared is equal to 1 minus sine squared. So we've got different forms of the Pythagorean identities. Become familiar with all of them. We can find the tangent and secant by dividing the original, the basic Pythagorean identity, each term by cosine squared. That will give us the 1 plus tangent squared equals secant squared, and we can easily turn that into tangent squared theta is equal to secant squared theta minus 1. Similarly, to get the cotangent, cosecant Pythagorean identities, we can divide each of the original by sine squared theta. And that gives us the 1 plus cotangent squared theta equals cosecant squared theta. And we can even turn that into cotangent squared theta equals cosecant squared theta minus 1. Quite a mouthful. But know all of these. Become familiar with all of them. Very important. Okay, so now let's take a look at, in general, simplifying a trigonometric expression. What that means is we're going to start by writing each expression in terms of sine theta and cosine theta, and then we're going to simplify. For example, here we have cosecant theta times tangent theta, and cosecant is 1 over sine. Tangent theta is sine theta over cosine theta. And we can divide out the sine theta. And notice that I do have theta written after each function. It's not just 1 over sine, it's 1 over sine theta. But fortunately, those can divide out, and we're left with now 1 over cosine theta, which is good, but we can take that one step further and make it into secant theta. That is one simplified form for that expression. Here's another example. Cotangent theta is cosine theta over sine theta, plus the cosecant is 1 over sine theta, and the cosine is cosine theta, but it's common for us when there are a bunch of fractions around to also make something like that into a fraction, over 1. So let's see what we have. Cosine theta over sine theta plus cosine theta over sine theta. Nice. Well, each of these fractions can be rewritten as cotangents. So that equals cotangent theta plus cotangent theta. And, well, just like x plus x is 2x, this is 2 times cotangent theta. Pretty nice. Let's see what's next. Okay, again, write each expression in terms of sine and cosine and then simplify. We treat sine and theta kind of as the foundation functions, so that's why we keep going back to sine and cosine. So here we have cosine theta times times cosecant, which is 1 over sine, times cotangent, which is cosine theta over sine theta. When we put these together, let's see, the numerators multiply to become cosine squared theta, and the denominators are sine squared theta. And this is cotangent squared theta. And that's the simplified form. All right, for our next example, we have secant theta minus tangent theta. Secant, that's 1 over cosine theta. Tangent, that's sine theta over cosine theta. In this particular case, what we have are two fractions, and they have the same denominator. That means that we can combine them into a single fraction with that denominator of cosine. So it's 1 minus sine theta over cosine theta. We can't do anything with that to simplify. And by the way, 1 minus sine theta is not Pythagorean. It looks a little bit like one of the Pythagorean identities, but it's not because sine is not being squared. All the Pythagorean identities have something squared. Actually, every term is being squared. So this is it. It's simplified. And now to the next example. All right, let's look at this next example. Secant theta minus cosecant theta. Secant, of course, is 1 over cosine theta minus cosecant 1 over sine theta. This time, they do not have common denominators. So in order for us to simplify, we must combine them by getting common denominators. And in this case, the common denominator is actually both factors, cosine theta times sine theta. It doesn't matter whether it's cosine times sine or sine times cosine. They're the same. So, the first fraction, we need to multiply by sine theta over sine theta. The second fraction, we must multiply by cosine theta over cosine theta. And when we're done, they now have the common denominator. Like I said, they're written in a slightly different order. One's cosine, one times sine, the other sine times cosine. However, as a fraction, they are the same denominator. So we now can combine them into a single fraction. It's really important to know that when we finish this, we're not going to be able to simplify. We have our denominator cosine theta times sine theta in the denominator, but the numerators are sine theta minus cosine theta, not times. So we can't divide out anything. We can't divide out the sines or cancel out the sines. We cannot cancel out the cosines. In fact, let me just make sure that that's very clear. Okay, our next example, cosecant theta minus sine theta. Cosecant, of course, 1 over sine theta, minus sine theta over 1, really. Now this time, they don't have the same denominator, but there is only one denominator, sine theta, so the common denominator is sine theta itself. So the first fraction is fine, it's already got the sine theta. It's the second fraction that needs that denominator. So we're going to multiply only the second fraction by sine theta over sine theta. And they now have common denominators. So we have 1 over sine theta minus, this time sine squared theta over sine theta. And with a common denominator, we can combine them into a single fraction, 1 minus sine squared theta over sine theta. And that numerator is Pythagorean. That is cosine squared theta. And we write it over sine theta. And there's not much we can do with it from this point. So we'll just kind of keep it as it is and say simplified. All right. Next example. Cotangent theta, of course, that's cosine over sine. And like I say, when I say cosine over sine, we can't write that. We need to write cosine theta over sine theta. And likewise, tangent theta is sine over cosine, but we write it as sine theta over cosine theta. That angle measure, that argument is required. Now these two fractions, again, need a common denominator. And this time, the common denominator will be the sine theta times cosine theta. So the first fraction has sine theta. It's missing the cosine. So we will have to multiply that in by, not by cosine, but by cosine theta over cosine theta, both numerator and denominator. And in the second fraction, we multiply that by, we need sine theta, so sine theta over sine theta. I'll do that in red. And let's see what we get. Now we do have common denominators, so let's just write this as one large denominator, one fraction of the sine theta cosine theta. And the first fraction, when we multiply the numerators, we get cosine squared theta, then the plus sign, and then sine squared theta. And whoa, nice. That numerator is the Pythagorean identity, becomes just 1. 1 over sine theta times cosine theta. Now, this is fine as it is. That's a lot of work we got getting here, especially since this is kind of an introduction into simplifying trig expressions. But you know what? We could, I mean, like I say, that's fine as it is, but we really could take it a step further. It's hard to know whether it's required or not. You might want to just ask your instructor. But if we did take it further, we could split that into two fractions multiplied together. We could make that 1 over sine theta times 1 over cosine theta. And then each individually can simplify. 1 over sine is cosecant. So we get cosecant theta times 1 over cosine is secant theta. That's something else we could have done with that one. Okay. Sine theta times tangent, which is sine theta over cosine theta, minus cosine theta. And we can write the sine theta and cosine theta each over 1. And let's see what we have when we combine the first two fractions. We've got sine squared theta over cosine theta and minus cosine theta over 1, of course. This time the common denominator is cosine theta. So we're going to multiply the second fraction by cosine theta over cosine theta. And now they will, basically that we have a common denominator here. And that common denominator is cosine theta. And in the numerator, we get sine squared theta minus cosine squared theta. Now this looks Pythagorean on the numerator, but it isn't. It looks like we should do something with the Pythagorean identity, but it isn't. So, and we cannot cancel cosines because we cannot divide out a cosine. So basically, we're done. So I hope this has been helpful to you, and I hope that you get a lot of chance to practice simplifying these trig functions. And for now, I'll say so long.